Next speaker, Mr. Mohammad Jawad Ashraf. He is a graduate of Center of Excellence. He will be talking about to assess the effectiveness of chute blocks and end sill in the stilling basin of Tomsa barrage. Mr. Jawad, same instruction to you. Please conclude within 10 minutes so that we can go ahead with other presentation also in time.
Am I audible to everyone?
Yes, Jawad, I can get your voice and your screen is also visible. Go ahead.
Okay, Bismillahirrahmanirrahim. Thank you for having me, first of all, and appreciation for the organizers of this conference. The topic of my presentation is to assess the effectiveness of chute block and end seal in the stilling basin of Tomsa barrage. Basically, we are going to assess the effectiveness of these auxiliary devices which are used to dissipate the excessive energy in the stilling basin of a barrage. So barrages are the structure, as you all know, that regulates the flow of a river, and they divert the river water into the off-taking canal. They may be termed as small dams because they temporarily raise the level of water. So these barrages are associated with the phenomena of retrogression, and this has been major concern in Pakistan, as we have witnessed in case of Jinnah barrage and Tonsa barrage. It is basically retrogression is caused by the surface flows, and this is actually a natural phenomena, but the excessiveness of this phenomena can lead to the structural integrity danger to the structural integrity of the barrages. So in case of Tonsa barrage, we have witnessed that since its anticipation in 1954, excessive retrogression has been reported, and this was rehabilitated for many times, but finally in 2004 and 5, a study was carried out by the consultant, and it was proposed that we may establish a subsidiary weir downstream of the barrage at the distance of 925 feet of the main weir. Along with the establishment of subsidiary weir, auxiliary devices were also introduced in the stilling basins. These include the chute block and the dentated end sill at the end of the stilling basin. So today we are going to discuss the effectiveness of these auxiliary devices, that is chute blocks and dentated end sill, in the energy dissipation along the subsidiary weir. So the configuration of the stilling basin we have in Tomsa barrage is USBR stilling basin type 2. And these type of stilling basin are employed when the incoming Froude number is greater than 4.5. So for this, to assess the effectiveness, we have employed a CFD-based numerical modeling scheme using Flow 3D software. And for this numerical modeling, we have the two geometric configurations. One is the barrage subsidiary weir and chute block and end sill, and the other one is barrage with subsidiary weir, but without chute block and dentated end sill. So this is the methodology we have employed for the carrying out the study. The first thing is the preparation of 3D model in AutoCAD, because the Flow 3D requires 3D modeling files that is .stl format to which are imported into Flow 3D, and then simulations are carried out on them. So these geometric configurations were initially modeled in AutoCAD, then they were converted into .stl format, and then they were imported into Flow 3D. Then the other step is the adding the boundary conditions, initial condition, physical parameters, and the turbulence model. So for reference, I would like to share the geometric configuration we have. This is the first geometric configuration in which we have the end sill, subsidiary weir, and the chute block. And this is the sectional view of the first geometric configuration, in which we can see there is an end sill, chute block, and the second geometric configuration we have is this, in which we can see that we don't have any chute block or end sill in this stilling basin. Okay, so for boundary conditions, we have employed the symmetry boundary condition, that the Y minimum and Y max, and the specified pressure conditions at other four boundary conditions, that are X minimum, X maximum, Z minimum, and Z maximum. There were four flow scenarios which we have counted in this study. They are 100% of the design flow, 90% of the design flow, 75% of the design flow, and 50% of the design flow. All these scenarios are apparently termed as the high flow scenarios, among which 100% is the ungated flow, whereas 90, 75, and 50% are the gated flow scenarios. So in order to assess the effectiveness, we have utilized four flow parameters for each of the scenario. So in case we have the total 8 simulations, and for each of the 8 simulations, four flow parameters were discussed. These are the depth average velocity, Froude number, flow depth, and the total hydraulic head. So now moving to the results and discussion. This is a table in which there is a summarized table of all the flow parameters we have evaluated for each of the scenario. Let's discuss it one by one. The first one is flow depth, and flow depth has been evaluated at four locations, that is before jump, before hydraulic jump, after hydraulic jump, start of the sealing basin, and at the end of the sealing basin. So we can observe that after the removal of chute blocks, the flow depth has been decreased in the before jump scenario. Similarly, it has also been decreased in the after jump, where the chute block has a higher flow depth and the removal of chute block has the lower flow depth. Similarly, at the start of sealing basin, we have seen that the flow depth is higher in case of chute blocks, whereas in the absence of chute block, the flow depth is lower. When we see about the depth average velocity, we have witnessed that the phenomena is opposite as compared to flow depth, as in the absence of chute block.
Time warning, please.
Yes,
Last
sir.
minute for you.
Okay, sir. I move to conclusions. From the conclusion, we can have that the absence of chute, in the absence of chute block, the flow depth increases. The flow depth decreases, the average velocity increases, and the total hydraulic head, that is the total energy in the absence of chute block, is comparatively higher for lower flows, and it is apparently same for the higher flows, that is 90%, 75%, 100%. These auxiliary devices are apparently not very much efficient, but for lower flows, when we have seen in case of 50%, they have a great impact on the effectiveness, on the amount of the total hydraulic head or total energy which they dissipate. So these auxiliary devices does not perform well for the higher flows, but they perform good when it comes to the lower flows, that is less than the 50% of design flow. So that's it, sir. Thank you.
Thank you very much, Engineer Jawad Ashraf.